So I went about making final exam problems. Before I jump into that, I want to talk about the schedule. And so we covered Lab 9 last time. And so there's one more lab to cover. That's Lab 10. And I decided to omit Chapter 7. So you don't need to read Chapter 7. And I've canceled all of the Chapter 7 exercises. But if you do Chapter 7, you can do it for extra credit. So you can still submit. If you go into Blackboard and submit a report, you'll see that the old Chapter 7 exercises are available as extra credit. So this final lab is to build a tic-tac-toe program. And so we'll look at that later, maybe on Wednesday. We'll look at that on Wednesday. And what I want to do today is to do the practice, take a look at the problems that I put together that will resemble the problems that appear on the final exam. So I pasted just now my document into this web page here, the practice final exam problems. So if you have your computer with you now, you can see that. Are there any questions about the about the course, the final, or anything? Nothing? All right, let's take a look at this. And by the way, these are questions that would be added on to, say, the midterm, the questions that appeared on the midterm. So these are questions that are related to the material that we covered after the midterm, but material before the midterm will also appear on the final exam. So a good reference of practice problems for that would be the midterm itself. All right, let's just go through here and do these. Actually, I'm going to bring up my document here. All right, so there's a figure 1 here. There's a declaration of a function called maximum. And it takes 2 arguments. It takes an array called A of type double. And then it takes an integer called number of elements. And the function returns a double, which is a floating point number. So let's read the statement here. Provide an implementation of the maximum function whose declaration is shown in figure 1. The first argument of the function is an array of double, and the second argument is the number of doubles that are in the array. The function returns the largest double that is in the array passed into it. Maybe that's, I could just say, that's a little easier to read. The function returns the largest double that is in the array. So we need to implement the function. So I'll just do it here. So I'm just going to redeclare this. And then I'll just create a function body to type in the implementation of the function. So we need to find the largest. We need to find the largest element in the array. So that means we need to scan through the array. So we need a loop. And you can use a while loop, but a for loop is ideal here. Remember, the first position in the array is 0. So we start the index I at 0. And the array has number of elements. So that's passed into the function as a separate argument. It's different than vectors. If we were to implement a function that took a vector, we wouldn't need to pass in the number of elements as a second argument. Because the vector is a complex data type. And it has many functions built into it that we can invoke. And one of the functions that we can invoke is the size function. So that's how we get the size of the number, that's how we get the number of elements that are stored in the vector. But for an array, that information is not a part of the array data type itself. So we have to, that information has to be maintained separately from the array elements themselves. So there's a loop that scans through the array. The index ranges from 0 to 1 to the number of elements minus 1. And so what we need to do is this is the standard way to solve this problem. What we do is we start with the first value in the array and say, okay, let's look at the first value, and well, that's the largest number we've seen so far. So let's store that as the candidate largest value. Now let's look at the second value. Is the second value larger than the candidate largest value? If it is, then let's set the candidate largest value to the second number. And then let's go to the third value and compare that to our candidate largest value. And we do that through the entire sequence, and then we can determine, which one is the largest. So that means we need to keep track of this candidate largest value. We'll call it K. And we can set it equal to 0, A of 0 rather. Oh no, I'm sorry, it's a double. So we'll call it like this, we'll call it the largest value. We'll start by guessing that the largest value is the double that's stored in the first slot. So that means we don't need to look at the first slot anymore. We'll start by looking at the second slot, which is index 1. Let's compare what's in A of I with our largest value, the largest so far. If the value at I, at position I, is bigger than our current largest value, then that becomes the new largest value. When we're done the loop, we return the largest value. That's the algorithm. Any questions about it? Once you get used to this, kind of understanding this, then, basically what you're doing is you're deriving algorithms. And so, learning how to do that takes a little bit of effort. in the beginning and experimentation. But once you get the hang of it, then you can build on that skill and solve more complicated algorithms. All right, I'm going to move forward. Let's look at figure 2. And I'm going to put a page break here. So here we have the same thing. It's another declaration of a function. And we're asked to provide an implementation of the function. The first argument of the function is a vector of int, and the second argument is the number of consecutive integers to append to the vector. The function appends onto the vector v the values 0, 1, 2, ... n. So n is some variable. Use the pushback function of vector to append these values to v. All right, so we're implementing the function. So we have a vector v. We don't know what's in v. Well, there's integers in v. It could have nothing in it. Could have a million integers in it. But our job is to append the values 0, 1, 2, and so on until we reach n. And we use pushback to append those values onto the back of the vector. Any suggestions? What kind of a loop do we use here? Use for loop, right? We know exactly how many times we need to repeat the pushback operation. How many times do we need, this is a trick question by the way, how many times do we need to repeat the pushback operation in this problem? N what? N minus 1? And n, and what's the other one? N plus 1, right? Which one is it? It's an off by 1 problem. Is it n minus 1? Do we call pushback n minus 1 times, n times, or n plus 1 times? N plus 1. Because we're starting at 0. So this sequence here has n plus 1 items. So there it is. We need to push n plus 1 values onto the back of the vector. So we need a loop that runs n plus 1 times. And convenient, the counter that we're using is going to double as the value that we push back onto the vector. Oops. That's it, right there. That was not too bad, right? Any questions about what's going on? Okay. Oh, I just copied this down here because I think I'm going to need something like this. All right, here's problem 3. This doesn't have a figure, so there's no pre-supplied code with this one. Suppose a vector contains a sequence of integers ordered from lowest to highest. A sequence of integers ordered from lowest to highest. For example, V might contain the values 3, 6, 7, 12. So that's lowest to highest. So we wouldn't have 3, 7, 6, 12, right? That wouldn't be in order. So these values are in order. They're ordered from lowest to highest. Write a function insert that takes this vector v as a first argument and an integer k as the second argument. Well, before we read any further, we know that we need a function called insert that takes this vector v as the first argument and an integer k as the second argument. So let's record what we know at this point. The function inserts k into the vector so that it preserves the order of elements. For example, if v was, maybe that should be were, right? If v were 3, 6, 7, and 12, and k were 8, does that sound more natural? Were rather than was? Was sounds more natural, but my grammar teacher from 30 years ago would say you have to use were here, but maybe things have changed. I don't know. Was is okay, right? Alright, so if k was 8, then after calling the function, v would become 3, 6, 7, and 8, and 12. Is everyone clear about the problem? So it's not so clear. We can use a for loop. We can use a for loop. Right? You see how 8 is getting inserted in there? 8 comes after 7, but before 12. So we need to insert it there. Now the book talks about this. So hopefully you've all read this chapter. And the book talks about this, maintaining the order of a sequence. How to insert a value. So one thing we can do, let's look at it like this. We've got these values. We'll do it like this. Say 3 is in this slot. Let's suppose these are slots. Actually, let me do it like this. Use minus signs. So these are positions. No, I don't need that. And 3 is in the first position. 6 is in the second position. 7 is in the third position, and then 12 is in the fourth position. Now we need to insert 8. So what's the process that we use? Well, we only have 4 slots. So we're going to need to add a 5th slot. And then after we add this 5th slot, we are going to go backwards. And we want to put 8 in here. But if we put 8 here, the numbers won't be in order. So, and the reason we know that is because we're comparing 8 with this position, the last, this position 4, right, which is no longer the last index. It's now the second to last index. So we compare 8 to 12. If 12 is bigger than 8, that means we're going to copy 12 into the last slot, and and then stop at that point. And now 8. Now this 4 slot is now a candidate to place the 8. Is this a good place to put the 8? Yeah, it's a good place because 8 is bigger than 7. We already know that 8 is less than 12. We did that comparison already. So that means we put 8 in here. We put 8 in here and we're done. So that's what we need to automate. We don't have a vector with exactly 4 elements. We have a vector with some unknown number of elements. And we don't know if it's 3, 6, 7, or 12, but we know that they're in order. So how do we automate this? Well, we're going to need a loop. We start at the end, and then we work our way forward. But before we enter the loop, we need to add on that new spot, right? So we'll do V. And let's go ahead and push back K onto the end of the vector. So actually, what we're doing here looks more like this, because we have to put something on there. So let's put the 8 here. So we're at this point now. We pushed the 8 onto the back of the vector, and then what we're going to do is swap it with the element before it until it's larger than the element before it. So in this position, 8 is not larger than 12, but here 8 is larger than 7, so we can stop. So we need to keep track of where we are in the vector. Let's use an integer, and let's let I be. It could either be where the 8 is, or it could be where the thing that we're comparing 8 to is. And I'm going to use the thing that we're comparing 8 to. So here I is going to be the size of V. Actually, it can't be the size of V, right? It has to be the size of V minus 2. Because here the size of V is 5, and the index that we want is 0, 1, 2, 3. The size of V is 5, but the index that we want is 3. Remember the off by 1 problem here. Now we're off by 2. So I is going to be placed here. Here I will equal 3. Remember, that's 0, 1, 2, and 3. And we're going to compare where 8 is at, which is I plus 1, position I plus 1, to what's in position I. But we can't do that if I is less than 0. So while I is greater than or equal to 0, we can carry out this comparison. Because if I were to be less than 0, say minus 1, Well, there is no element at position -1. There's an element at position 0, so we need to include 0. So let's compare it. So if V is what we, well, let's just call it K. If K is bigger than V of I, if K is bigger than V of I, look at the example. K is 8, and here I is 3, so 8 is not bigger than V of 3. So this won't run. But in this situation, in the next iteration, when 8 is in this position and I is 2, then K is bigger than V of I. That means we're finished. So when K is bigger than V of I, we're done. Let's just get out of there. We're done. Not quite, but yeah, maybe that's right. This is right. But let's suppose that that K were not bigger than V of I. Then what do we do? So that means where K is, where 8 is, V of I needs to be placed there, and then 8 needs to be placed where I is. So we do V of I plus 1 gets K. And V of I, I'm sorry, that's not right. V of I plus 1 gets V of I, and a V of I gets K. Here, this is 8 is in I plus slot I plus 1. 12 is in slot I. We're comparing K, which would 8, K is in this slot, so we can use K there. We could use V of I plus 1 here. I'll say this is equivalent. We can do this. We can do that. I think I'm going to leave it like this. So let's look at this again. Here, K is in I slot I plus 1. So we want to write what's in V of I, the one before it, the 12, needs to get stored into where 8 currently is. Needs to go into position 4. So that's done here. That puts 12 into position 4. And this puts 8 into position 3. And then we've already analyzed what happens at this point. We're done. That's when this condition is triggered. That's harder than the other ones, right? What do you think about this one? This is, you can see it's automation, right? This is automating. If you want to get a machine to do something for you, you have to program it. If you want to get a robot to vacuum your floor in your house, you need to program it. And you're going to fill it with these kinds of instructions. It needs very precise instructions that are expressed in terms of numbers. Okay, that one's done. Any questions on that? A question? What am I doing there? Here I is being set to the index that's one before the last index. So this is here when V comes in, we add a value onto V. But actually, it doesn't matter if we pass in K here because we're not even using that. We could just push back a 0. Because we write K into the position there. Oh no, that's not true. This should be K because if K is bigger than, if this is true, then we need to have K in that spot when we return there. So what we do here is we add a slot onto V. So if V were to be 4, now V is 5. But this index I is going to represent the number that we're comparing 8 to, or K. So we insert K into the last position, see? We insert K into the last position. So we don't need to compare K to itself. We want to compare K to the position just before that last position. So the last position is size minus 1. See, the size is 5, and the last position is 4, because we start counting at 0. This is position 0, 1, 2, 3, and 4. So the last position is size minus 1. So if we want the position just before the last position, which is here, we need to take size minus 2. So this is where, remember, this is initialization. This is where I starts. Oh, we never decrement I. Sorry about that. We have to decrement I. So we're scanning the list of values from the end of the vector toward the beginning of the vector. And we're moving things forward. This 12 is getting moved to here. And then the 8 goes into here. So we're going to keep moving down until 8 is bigger than the thing before it, because then 8 is in the right order. You have the solution here, right? So if you don't get this now, then when you're at home and it's quiet and you can concentrate and work through it mentally and see if you can get it. Because this, I could just ask this question right on the final, then you're prepared for this. And the book covers this. So if you didn't get it in this lecture, you can try to get it by reading through the book as well. I know that's a hard problem. But you're the generation of people who are going to be programming the robots that are going to relieve you of lots of menial jobs in the future. I'm in the older generation, so I won't see that. But I'll tell you, this is what it's all about, is figuring out how to automate things. So this is automation. This is programming a machine to do something. All right, let's look at this one. Write a predicate function that checks whether two vectors have the same number of elements. A declaration of the function is shown in figure 3. The function takes references to two vectors as arguments. The function returns true if the two vectors have the same size, otherwise it returns false. Okay. This one is a lot easier than the other one. Maybe on the final I would skip that other one first and then go back to it later if I had time. This one is a lot easier. You know, I made up these problems. I was reading the book, and I made these problems up, you know, just looking at what the book was talking about. Okay, so this is actually one of the problems in the book. I think it's one of the, not a programming challenge, but one of the exercises. Oh no, maybe this is one of our assignments or something, right? It's a lab. Anyway, this is from the book. Oh no, this is not from the book. The next one is. Do the two vectors have the same number of elements? Does A have the same number of elements as B? That's pretty easy, right? How would you do this? How do you know if A and B have the same number of elements? You call the size function, and then you compare the size function. This is good just like that. But if that's confusing to you, then you can write it like this. That this expression is evaluated to true or false, and then that's what's returned. That's number 4. That one's the easy one. All right, this one is a development of the last one. So write a predicate function that checks whether two vectors are identical, i.e. they contain exactly the same elements in the same order. If they're identical, return true. If they're different, return false. Well, so I'm going to go through element by element. Is A0 equal to B0? Is A1 equal to B1? Is A2 equal to B2? And so on, right? But that procedure will work only if the A and B have the same length. So let's check first whether they have the same length. If the size of A is different than the size of B, then we know that they're not identical. We're done. Okay, at this point in the code, if we reach where the cursor is now, we know that they have the same size. So we can compare them element by element. We use a for loop for that. Start at index 0. And we're going to set I to 0. We're going to let I go through to size -1. So see, I is strictly less than a dot size. That means if the size is 5, I reaches 4, but I will not reach 5. And you can't do this on the exam, but I can do that here. I'm going to copy this. Well, actually, it's not. I'm not saving much here. If A of I is not equal to B of I, what do we do? What do we know at that point? Maybe A of 3 is 7 and B of 3 is 10. What do we do once we reach that point? We don't have to do anything else, right? We know. We know. They're not identical. Let's just get out of here. So we return false. One more thing to do. What's the last thing that we do? Kanika? Return true. Got it. Great. That's good. Yeah, you're following along there. That's great. Am I going too slow? No? Okay. So we return true. So we've passed all the tests. We've tried to find something wrong, something that didn't match. Everything matched, so we return true. So here we go. Figure 5. I think we have time for one more here. So is non-decreasing. This one's a little harder. Once again, it's an implementation of a function problem. That's what they all seem to be. Write a predicate. What does that mean? Predicate function. Predicate function. It means it returns true or false. That's what it means. Write a predicate function that checks whether a vector of integers, v, contains values that are in non-decreasing order. A declaration of the function is shown in figure 5. The function returns true if the elements are in non-decreasing order. Otherwise, it returns false. For example, it will return true for 3, 4, 4, 6, 8, because those are in non-decreasing order, but it will return false for 3, 4, 6, 2, 5, because, well, 2 comes after 6, so now it's decreasing. It's in a decreasing situation in that one slot. So, you know, we had to compare, let's see, non-decreasing. So this we got to compare items that are next to each other. And the item that comes after should be bigger than or equal to the item that comes before. So we had to range through the vector. So we need our index. And I don't know where to stop. I have to think about where to stop, because I might be off by 1 or 2 even. And so what we want to do is we check to see, we want to compare v of I to see if it's less than or equal to v of I plus 1. We want that v of I to be less than or equal. We want that to be true, right? So if it's true, we don't know anything. We have to keep looking. But if it's false, if it's false, if v of I is bigger than v of I plus 1, if a number is bigger than the one that follows it, then it's decreasing, which means it's not non-decreasing. So at this point, we know we have our problem, so we can return false. We don't have to finish looking any farther. But if we compare every pair of numbers and we never return false, then we can return true at the end. But here's the question. What goes here? Think about that right now. Let's get it figured out. 2? I have a 2. I have a 1. Anybody with a 1? Anybody with a 0? 1? There's a 1 back there. 0? I'll take 0. Right. All right. Now let's analyze it. If it's 0, then I is going to be less than size, which means I can get as big as size minus 1. Let's suppose the vector. Let's do this. Let's suppose this. Let's suppose that that v dot size is 8. Okay. Or 4. Maybe that's easier. Or 3. That's easier. Let's suppose that v dot size is 3. That means the valid indices equal 0, 1, and 2. Those are the valid indices. Position 0, position 1, position 2. Because we have 3 items. So if I gets as big as it can, that means it's, and let's analyze 0 first. That's my choice. If I gets as big as, I cannot get as big as 3, but it can reach 2. Right? So if I were to be 2, then we would compare v of 2 with v of 3. V of 3. There is no v of 3. Right? We're going too far. We have to back up. Let's check. Let's try 1. So if I gets as big as we let it get, how big can I get in this case where size is 3? Well, it has to be less than 3 minus 1. 3 minus 1 is 2, so it has to be less than 2. That means at most it could be 1. So the biggest that I is going to get is 1. That means the biggest this is going to get is v of 2. That's it. That's the last element. So we go through the vector and we compare. Every element gets into a comparison. And we can't go any farther than this. The answer is 1 there. So we've got to go up to size minus 1. See, I took a simple example, 3, and I analyzed it just to make sure I could get that off by 1 problem solved. That's how I do it. Maybe you can do it. You might be able to work in the abstract and just let it be size, you know, and think about it that way. That would be good too. And all right, that's. I have teaching evaluation form that I want all of you to fill out, and that's why I'm going to break early. And next time, hold on there, David, before you get started. I'll just keep talking. Next time we meet, we can decide what to do.